Hello, so in this video we're going to look at areas under curves, right? So when we have a graph, the area under the curve. So last time we looked at definite integrals. So for example, if we were to work out between 1 and 4 of, let's say, x cubed dx, what we said was we integrated it first, so it'd be a quarter x to the 4. But then we do the two limits, right? So we don't need the plus c, we just because we're going to substitute between these two limits, between 4 and 1. So that meant we basically just substitute 4 inversed, so a quarter of 4 to the 4, then a take away, then a sub in 1, so the lower limit, a quarter of 1 to the 4. Then if I work that out, I got 64, take away 0.25, and that would give me 63.75. okay, so these definite integrals give me a number. Okay, just gives me a number, not a function or anything like that. It gives us just one number. So what is this number then? And I did very briefly talk about it last time, but this number, well, if we were to sketch the x cubed graph, right, let's say over here. So the standard x cubed graph looks something like this, something like that, right? Y is x cubed. And so then if we say let's say 1 is here, and then let's say 4 is there. Obviously, that because why I'm choosing 1 and 4 is because that's my limits, 1 and 4. So this number then, 63.75, actually corresponds to the area here, right? If I shade it, cool. The area between the curve and the x-axis, right? The area under the curve, okay? That area that I've shaded between these 2 points, so the limits correspond to the endpoints of my region, okay? The endpoints of my area. So the area is, well, 63.75, and that is what a definite integral is working out. The area under the curve, between the curve and the x-axis, that area, that space between these 2 points, okay? And so yeah, so definite integrals tell us the area between a curve and the x-axis, okay? And you can see that with this example here, okay? And this actually stems from also the fundamental theorem of calculus. It's a bit deeper than obviously we need to know at A level, but just some backstory. This is why this works. Why the integral here tells me the area is due to the fundamental theorem of calculus. So I did say at the start of this chapter, the fundamental theorem of calculus tells us that integration is the opposite of differentiation. It comes in 2 parts, okay? So the first part of the theorem is indeed that integration is the opposite of differentiation, but the second part is this area here. The second part tells me that integration and areas under curves are linked in this way, okay? So this is the second part. So that's the backstory, okay? Obviously, if you go on to do maths at uni or whatever, more deeper, you should meet the fundamental theorem of calculus, and you'll see why that works. But for now, this is just what we're going to do. We're going to work with definite integrals, as in this example, which gives me the area between 2 points under the curve, okay? Right, so let's have a look at some examples then. Okay, so we've got this one first, and we're given a graph, and we're told the graph shows parts of the curve with equation y is x squared of 2 minus x. The region R, which is shaded right here, the grey area, is bounded between the curve C and the x-axis. So it's the area under the curve between where? Between 0 and 2, okay? And we need to use calculus. Remember, calculus means differentiation and integration. Well, we're going to need to use integration here to find the area of the region R, okay? Right, well then, what we need to do, as we just discussed, we need to find r by translating it into an integral, okay? So the area is going to be an integral, it's going to be an integral with limits. So what are the endpoints of my region? Well, 0 and 2, okay? So we're going to integrate between 0 and 2 of the curve, the function of x squared of 2 minus x dx. So if I work out that definite integral, that tells me the area under the curve between the 2 points, which is the region R, okay? So we need to work out this integral then, which we've worked out in the last section. Well, firstly, we're going to need to expand the bracket here. We can't integrate it yet. We need to simplify the integrand, what we need to integrate. Okay, so expanding this, again, it'd be between 0 and 2. If we expand the bracket, we get 2x squared, take away x cubed, dx. Now we're in a position where we could just integrate this, right, as we did last time, as we've done throughout this chapter so far. So we integrate this, do this integral, where 2x squared, firstly, that would go to 2x, then we add 1 to the power to get cubed, then we divide by 3. And then minus x cubed, well, that would go to minus x to the 4, because add 1 to the power, 3 add 1 is 4. Then we divide by 4. And we don't need a plus c here. You can do, but it's quite redundant because the c will go away to 0 at the end. We saw that last time as well, because we're working with limits. When we substitute the limits in, we don't need a plus c. So we're between 2 and 0, and at this point then we're going to firstly substitute 2 in. So that'd be 2 over 3 of x cubed. That'd be 2 cubed. Take away a quarter of 2 to the 4, right? Then we're going to take away, and then we're going to plug in the lower limit 0 in. So that'd be 2/3 of 0 cubed. Take away a quarter of 0 to the 4. So if we work all that out in the calculator, that should get me 4 over 3, 4/3, okay? And that's my area, and we could give the units. We don't know what the units are, so we just call it units squared. Again, the squared meaning it's an area, right? It's like, for example, if a rectangle has area 3 by 5, the area would be like 15, right? Centimeters squared, for example, if that was in centimeters. The unit squared means it's an area quantity, okay? We don't know what the units are. Obviously, it's just a general. You don't have to even give that. You can just leave my answer as 4/3 if you want to. Just leave it 4/3. But we can add that on to represent units. When you work, for example, you'll see this a lot when we do mechanics, if you haven't already. When we look at, we can integrate, for example, a velocity time graph to give me displacement, right, or distance. And that has, it could be in meters or meters squared or something like that, right? So the area under the curve is quite useful, especially you'll see it in mechanics. Where it gives me displacement or something like that, right? So there is a purpose to this, but for now, I just want to work out areas under curves, right, using integration. So yeah, so that 4/3 tells me the area is 4/3 between 0 and 2, okay? And yeah. Okay, so we've got this question now. We need to find the area of the finite region between the curve and the x-axis, okay? Okay, they're not giving us a sketch. Very, very, very helpful, especially later on, where it would be quite important to visualise what's going on with the curve, because the area can get a bit more complicated. But for now, it's helpful to sketch to see what's going on, to see where my region is. We need to sketch this, right? So y is 20 minus x squared. I'm going to rearrange it so it's higher powers first. So the x squared term first. So minus x squared minus x plus 20. I'm going to sketch this curve. It's a quadratic. So remember, we should be able to sketch quadratics. We've seen that before. So firstly, the negative x squared coefficient means it's going to have a frowny shape, a negative shape, right? Okay, I then need to find the roots. Okay, so we need to set this to 0. This quadratic equal to 0, as that gives me my roots. So if I, let's say, use the formula because I'm lazy to try and factorise, so x would be 1 plus or minus the square root of minus 1 squared minus 4 lots of minus 1 of 20 over 2 lots of minus 1. And so that, if I put that in a calculator, I should get the roots. X is 4 or x is minus 5. Okay. So now I've got a very good idea of what my graph will look like, right? So it has a frowny shape, and it has these roots. So x is 4 would be, let's say, there. Minus 5 would be there. So it's going to look something like this, right? Okay. Let me add between 4 and minus 5. Okay. Obviously it's not asked for sketch. I don't need to add the y-intercept. I don't need to find like the turning point. I'm not that fussed about how detailed the sketch is. I just need a rough idea of what it looks like. But there we are. Cool. So the area of the finite region between the curve and the x-axis is actually going to be this region here between minus 5 and 4. Okay. Right. Hopefully that made sense. It wouldn't be that area down there because actually the curve will keep going down. So the area would just keep going on and on and on, right? So it's only between the x-axis and the curve has to be that region there, okay? Okay, cool. So how are we going to find that region then? If we use integrals, we could say the area then. Well, the area between where? Minus 5 and 4, right? That's what we're working with, between x is minus 5 and x is 4. And then we're going to integrate the curve. So the curve has this expression, right? Minus x squared minus x plus 20, lots of dx. Right, then I can integrate that. So, okay. Okay, minus x squared. Well, if we add 1 to the power, or minus x, add 1 to the power, we get minus 3. Then it'd be divided by 3, okay? Then minus x, well, that would go to minus x squared, then divide by 2. And then 20, well, that'll just go to 20x, right? When we integrate every term, so that's integrated. And that would be between 4 and minus 5. Okay, we can simplify the fraction a little bit, make it look a bit nicer, to be minus a third x cubed minus a half x squared, add 20x between 4 and minus 5. Okay, now it's just a case of substituting stuff in. So that would be if I substitute 4 in first, as it's the upper limit. So if I sub 4 into here, that'd be minus a third of 4 cubed minus a half of 4 squared, add 20 lots of 4. Then I'm going to take away, then I'm going to plug in minus 5, take away the lower limit. So minus a third of minus 5 cubed minus a half of minus 5 squared, add 20 lots of minus 5. Okay, so if I plug that in, if I substitute that in, put it in a calculator, I should get I should get 243 over 2, okay, and that would be my area in units squared if you want to be a bit more specific. But that number then represents the area of the curve I've shaded, okay. The area there that I've shaded between minus 5 and 4 is 243 over 2. Okay, cool. Okay, right, I'm going to get rid of this now to to make more room. But we've got this exercise question then. We are told here that the shaded area under the graph of the region, you can see it in yellow hopefully, between 0 and k. This curve here of 3x squared minus 2x plus 2, the shaded area in yellow, bounded between the curve and the x-axis, you can see that, right? And the lines x is 0, x is k. The area is 8, okay? Area is 8. We need to work out the value of k, so actually we're going in reverse now. We're told the area, but now we need to find one of the missing limits, okay? Alright, okay. Well, how would we express the area, right? But we know the area is 8, but how would we express it as an integral? Right, how would we work it out? Imagine we didn't know it was 8. How would we work it out, right? So, again, it's between 0 and k, right? This area here in yellow. So, between 0 and k, we're going to integrate the function 3x squared minus 2x add 2, okay? And that should give me the area between 0 and k underneath the curve, right? Cool. So we'll just integrate it then, right? Again, k, don't freak out, we don't know what k is, but k is just a number, okay? So we can integrate just as we normally do. So firstly, we're going to integrate what we've got in here. So 3x squared will go to, well, 3x cubed, then we divide by the power, divide by 3. Then minus 2x, that will go to minus 2x squared by adding 1. Because again, hidden power of 1 in x, add 1, we get 2. Then we divide by 2. Then 2 is just a number, we just tag an x on. Okay, then we're integrating between k and 0. Cool. Right, we can simplify the fractions to help. Simplify what we've got inside here. Well, 3 over 3 just goes to 1, so it'd be just x cubed. Then minus 2 over 2 just goes to minus x squared plus 2x. Okay, a lot more cleaner. So now we're going to do what we normally do, substitute k in first. So it'd be k cubed minus k squared, add 2k. Then we're going to take away, going to substitute 0 in. So it's going to be 0 cubed minus 0 squared, add 2 lots of 0. Well, that will all go to 0, right? So that would just be k cubed minus k squared, add 2k. Right. We're told, okay, so that's my final expression. So that's the area, right? But we're told the area is equal to 8. So this whole thing has to equal 8, right? So k cubed minus k squared add 2k equals 8. Right, so we're going to have to move the 8 to the other side to get k cubed minus k squared add 2k and minus 8 equals 0. Right, okay. We're in a bit of a pickle. It's not a nice cubic to solve. We're going to have to probably resort to just trying to find a solution, right? And actually, we don't have to trial it because we've got the calculator to help us here. What you'd have to do is just substitute various numbers of k. So k is 1, k is 2, k is 3, maybe k is minus 1, minus 2. You know, you have to start guessing solutions at this point. But the calculator, we don't have to do the guesswork because the calculator will give me the solution if I use the cubic solver function in it. So the degree is 3 of the polynomial. And actually I get k is 2. And then I get these other two solutions, minus a half, add 1.93, blah, 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 I. Okay, I did briefly mention it last time. This I, for A level, it means imaginary, but it basically means it's not a real solution. Okay, if you do further maths, you'll look at it there, but you need to know that when you see this weird I, the calculator might give you as a root, it's not a real solution. It's not a viable solution. So that's not. So actually, the only solution we get is k is 2. Okay. But you need to show it's 2. Again, always be very, very hesitant when you just use the calculator and write down the answer from your calculator. You should show you're working. So how we can show it is, well, just substitute it in and see if it equals 0. So k is 2 because If we sub 2 into here, we get 2 cubed minus 2 squared plus 2 lots of 2 minus 8. If we work that out, put it in the calculator, we should get 0, okay? So that means k equals 2 is a solution. And that'd be the only solution. And that makes sense because it says work out the value of k, indicating it's only one solution possible. Okay, that's really it, okay? So there we are. That's the value of k. So you can work backwards, right? We can work backwards. If we're given the area, we can use integration to work out a missing limit, right, as we just saw there. Okay, I've got this exam question to finish off with. It's quite an interesting one because we're told, we're given a sketch, right, of this curve here, 2x cubed minus 17x squared plus 40x. Cool. We're told it has a minimum turning point. Now that's where it gets interesting. It has a minimum turning point at x equals k. You can see that here, right? It's a minimum point. That'd be a maximum, but we don't need to consider that. So it links differentiation quite nicely that we looked at last chapter. We're told the region R, then we're told it's bounded between 0 and k. You can see that here. It's between 0 and x is 0, x is k. The area underneath the curve, okay. We're told we need to show the area as this, 256 over 3, okay. So we need to get to the area, okay. Well, firstly, we're going to need to find k, right? Because the area, well, how do we work out the area as an integral, right? It's between x is 0, and x is k, right? So that's my limit between, and then we're going to integrate 2x cubed minus 17x squared and 40x. My problem is I don't know what k is, so I'm not going to get a numerical answer. I'm going to need to find k before I integrate. That's where this comes in, this information about turning points. So if it's a turning point, by the way, a turning point also is a stationary point. What do we know about stationary points? Hopefully should be alarm bells, which means that dy dx has to be set to 0, okay? Any turning point, stationary point has to be set to 0, okay? Right, so the derivative is 0. Well, in order to do that, we need to find the derivative. So again, we know that y is 2x cubed minus 17x squared and 40x. So we need to differentiate, right? So we looked at how to differentiate expressions like this last time in differentiation. Fairly nice sort of expression. We don't need to use index laws to simplify. So we can just differentiate. Well, if we differentiate 2x cubed, well, we times by the power, we move the power to the front, so 2 times 3, which is 6 x, and we knock 1 off the power. 3 take away 1 is 2. Then, like the same with 17x squared, minus 17, we bring the power to the front, so times that by 2. Minus 17 times 2 is minus 34x. Knock 1 off the power to get 1. Well, that's just x, and x to the power 1 is just x. And then 40x, well, that just goes to 40, right? Okay. That's my derivative. I now need to set that to 0. So 6x squared minus 34x plus 40 equals 0. Okay. I can't simplify anything, I don't think. I can't cancel anything down. I'm just going to use the formula then, right? I'm going to write down the formula. So x is 34 plus or minus the square root of minus 34 squared. Take away 4 lots of 6 lots of 40 divided by 2 lots of 6. And that shows my working, right? It shows how I get my roots. And now I can use the calculator to give me the roots. So we get x is 4, or x is 5 over 3. Okay, So that tells me there are two turning points then, right? Where x is 5 over 3, x is 4. That makes sense because we actually got two turning points on my diagram, right? Remember, that was a maximum, this is a minimum. So actually, if we look at my two solutions then, let's look at k. K, the minimum is on the minimum point. That's the second stationary point, right? This is the first one. This is going to be the second one. Which means, with my two solutions, this is my first value of x, that's the smallest one. That's going to be my maximum, and that's going to be my minimum, as you can spot here. That corresponds to the maximum and the minimum point there. Which means k would be the second one, the larger one. That would be k then, right? X is 4. So therefore k would equal 4. Okay. Hopefully you can understand that. So now I found k. That's great news. Now I know what k is. I can work out my area. Right? I can simplify this integral. So therefore my area is going to be between 0 and k, which is now 4, of 2x cubed minus 17x squared, add 40x dx, right? And at that point now I'm integrating. I'm just working out the integral as I usually do. Well, 2x cubed, that would go to 2x4. If we add 1 to the power, divide by the power. Then it's minus 17x squared, we add 1 to the power to get x cubed, then divide by 3. Then 40x, we add 1 to the power, well, power is 1. So it'll be 40x squared, divide by 2. And that'll be between the limits 0 and 4. Right? And at that point, we're just substituting stuff in. So substitute 4 in first. Actually, no, we can simplify, right? So if we simplify the fractions inside, where 2 over 4, that's going to be a half x to the 4. 17 over 3 doesn't simplify, so that's just 17 over 3, x cubed. And then 40 over 2, x squared goes to 20. Between, do I have any room here? Oh. There we are, between 4 and 0. Now I'll substitute it in, right, after simplified it. So it'd be a half of 4 to the 4 minus 17 over 3 to the 4 cubed plus 20, lots of 4 squared. Then I'm going to take away, then I'm going to substitute 0 in it. So it's going to be a half of 0 to the 4 minus 17 over 3 of 0 cubed, add 20, lots of 0 squared. Now, I guess a question you might ask is, why bother even showing that and plugging 0 in? Because it will just go to 0, clearly. You do need to show you're working, right? You need to show you're clearly substituting it in, because it shows you understand what the process is going on here with these brackets, and that we're substituting the two limits in, even if it's a bit redundant, right? Anyway, so if we do all that in the calculator then, we plug all that in my calculator. We should get 256 over 3. And that would be the area of R. Okay. Oh, and there we are. 256 over 3. There we are. We've shown the answer is indeed 256 over 3. Cool. Okay. Nice little question at the end. A bit of link into differentiation. They do tend to do that sort of stuff sometimes. You need to, find a particular point before you go and integrate and find the area. But yeah, that's it for now. Hopefully you're confident with kind of just finding areas, what the integral is doing between 2 points. It finds the area under the curve. Okay, so I'll see you next time.